right. My name is Scyller Borglum, and I am the underground storage market leader in our energy national business line. In the United States, we have our business broken out in operations and then in strategy and business development. So I'm on that side of the business, but I do work in lockstep with the fine men and women who comprise our energy storage services group. Prior to working at WSP, I worked in the oil fields up and down the Rocky Mountain front. I am very excited to tell you that this pivot in my career has been one of nothing short of mind-blowing, because it landed me precisely in the energy transition, in the middle of energy policy, in the middle of energy development, exactly where I wanted to be and exactly what I had been studying all these years for. I conducted geomechanical studies on various rock and salt types while I was in graduate school at the world-renowned geomechanical lab at RESPEC. And I co-authored the book, textbook called The Fossil Fuel Revolution, Shale Gas and Tight Oil. I have 2 books coming out. This one coming out this year is on STEM study habits, and then in early 2024, the Underground Storage Technical Guide. In my engineering career, I did have a quick dog leg over into politics. I was elected as representative in South Dakota, so I served in our state legislature, where I assisted with bills and policy discussing and pertaining to mainly the advancement of renewables, so solar and wind. And then, just so you know where I'm at, I live in Rapid City, South Dakota with my husband, but I frequently travel, or commute rather, to Houston for work. So let's talk a little bit about what we're thinking on today. I'm going to first talk about our energy storage services from WSP and what we do. I'm also going to give a brief primer on our underground storage, specifically salt cavern development. And this is so that you understand why we're discussing what we're discussing in the remainder of the presentation, which is going to be compressed air energy storage. We'll use a brief case study for a salt cavern that we're developing currently that I think will be very interesting for you. And then the bulk of our work will be on the Huntorf case, which is 40 years old. And you might be asking, why are we discussing something at a global lunch and learn that has been documented and discussed and studied ad nauseum? But there's some good reasons why we're revisiting this incredible facility now. We will then discuss innovations and takeaways, and we will end with a Q&A. So energy storage services, what is it that we do? At WSP, I work, as I mentioned in the introduction, with a group of about 125 engineers and scientists who do just tremendous work throughout the United States. We handle all of the underground injection control wells, which include your salt caverns, your saltwater disposal wells, leaching plants. We do industrial disposal wells. Of course, we do carbon capture and sequestration and acid gas wells. Those would be your class 2 permits if you're familiar with those. We develop and help maintain natural gas reservoirs. We do well permitting and geologic studies and facility operation. We have done the bulk of the salt cavern development in this country from the very beginning. So salt cavern development and underground storage started in the United States in the late 1950s, early 1960s. And that was advanced when in the 1970s, there was the oil embargo, and we needed a place to store our crude oil for our National Strategic Petroleum Reserve. Those caverns that were selected had previously been used as salt mines, and some were in better shape than others because they weren't designed specifically to hold liquids. They were designed to mine for salt. And where my company, and now as a part of the larger WSP, got its start was in the developing and designing and ensuring the cavern integrity of that National Strategic Petroleum Reserve. So we have been in this business now for nearly 50 years, and we do everything across the board from your front end engineering design. We do, as I note here, the well permits and geologic studies. we drill, we do the leaching, drilling, as you'll see on the upcoming slides, and leaching, that's the bulk of the specialty work. And then of course, if clients need us to also maintain and operate their facilities, we can do that. That's a smaller part of our business because most of our clients operate and maintain their own facilities. So what is underground storage exactly? Well, in our world, there are about 5 versions that you can pick from when it comes to underground storage. The first and most common is going to be your salt caverns, and that's because we treat salt like an impermeable material. It's about as close as you can get, but we also know that in fact it's not a rock, it's a mineral, and this has its advantages. One of the advantages is when you drill into a salt formation and you need it to contain a liquid or a gas, these minerals tend to recrystallize over time, and some faster than others. This is because of heat and pressure. This has the added advantage of any damage that might have occurred during the drilling process will self-heal. We have domal salts, which tend to be a more homogeneous and a purer medium, and then bedded salts, which are more up in the Central and North America and a little bit in the Northeast, and I'll show you a map of that here in a second. Those work as well. They just tend to be a little bit shorter and squattier, and sometimes they have inner beds, which can be a challenge when you're trying to leach. We also have the salt mines, so that would be your point B that you see here on this graphic, and those are mines that chemical companies have used to actually pursue the chlor-alkali so they can use it for their products, and then realize that these make great holding spaces, storage spaces, and so they get a second life out of these salt mines that they developed. Of course, we have saline aquifers. In this graphic, if you would envision it actually being quite a bit lower than what is shown here, the saline aquifers are not water that you would drink, you would not use in egg, it's not potable. And it's dirty, nasty water, millions of years old, but it makes a wonderful space for storing and sequestering carbon dioxide. We also have depleted oil and gas reservoirs. These are large known spaces, containment spaces that did once hold oil and gas, and now we can use them and give them a second life, either temporarily storing natural gas, or in some cases are being looked at to permanently sequester carbon dioxide. And lastly, we have hard rock caverns. These make terrific repositories for liquefied petroleum products, so your propane, your butane, and so these are fewer and far between. They're quite expensive, but the few in this country that we do have work very, very well. So let's take a look at salt around the world. I'm not going to take you on a geology lesson here, but the point of this slide is really to demonstrate that geology is neither uniformly accessible nor is it universally systematic throughout the world. And we know that intuitively, but the reason it's important for this presentation is because what we are looking at is a way to store energy. It isn't going to work for everybody, and it isn't going to work everywhere, but for those for whom it does, it is an unbelievable resource. So you'll notice in the American Gulf Coast, there's a lot of blue there. Those tend to be domes. Those are those larger, purer formations that I told you about, where we can make enormous salt caverns. We develop enormous salt caverns. And then going up the eastern side of the Rocky Mountains, you can see a number of bedded salts, and we do store products all up and down the Rocky Mountain front there. Not shown on this map, of course, because these are salt deposits, but the hard rock caverns are going to be in the northeastern part of the United States. So there is salt around the world, and certainly in locations where we find oil and gas, which is advantageous, and there will be reasons why we discuss that here shortly. So let's look briefly at salt cavern development. Salt cavern development has two phases. The first phase, you're going to drill into a salt formation, and that can take on the order of a month. All right. You use standard drilling procedures. So for those of us who come out of the petroleum engineering world, these skills and techniques are very similar. You go down to the depth that you planned, and then once you've done this, then you take your drilling rig off location and you begin the leaching process. The leaching process, you're going to first inject directly, and that will develop the bottom portion of your cavern. And after a time, you reverse the flow of your leaching, and leaching is pumping fresh water into your cavern, letting it come into contact with those salt cavern walls, dissolving the salt and increasing the size of your cavern. And when you reverse your flow, that's when you start developing the upper portion of your cavern, so you can get a nice cylindrical shape, which is geomechanically stable for storing liquids and gases. You'll notice that there's what's called a blanket at the top, and that would be something like a nitrogen blanket or diesel. And what that does is protect that salt roof so that you don't lose any of your salt at the top, because you depend on that for stability with your casing and your casing shoe. You've cemented in your casing up to that point, so you really want that to remain stable and well defined. Now, if you take a look at the image on the right, you'll see this is a current cavern that we are in the process of developing. And the reason I wanted to show you this is because even with the best of the design, the best understanding, the best geologic descriptions, we're still dealing with formations in the earth, and occasionally come across something that did not show up on any of our investigations, our preliminary investigations. So on the right-hand side, you'll see it's smoother and has a nice shape to it that we would expect. On the left-hand side, you'll see where it's a little bit lumpier and red. This is where we ran into some preferential leaching, because this was not pure salt, but had other entrained non-solubles in it. One of the points that you need to be aware of is that at the bottom of your cavern, you develop a sump. And this is where you let your insolubles fall, because they're not going to be dissolved in that brine that you return to surface. And so this is something that you need to know when you're developing a cavern. We're working with natural phenomena, and so they're not going to be exactly perfect, but we can still control the shape to a terrific degree through our experience and through the technology available to us. So this is a current salt cavern that we're developing for gas storage in Texas, and so it's just a remarkable piece of work. Okay, so now let's talk about compressed air energy storage. Compressed air energy storage uses electricity that's produced at night or in low usage times, and it compresses the air and it stores it underground. As you can imagine, you need a robust storage containment system because the pressure is quite high. And then when the electricity is needed during peak hours, you release that compressed air, it expands, passes through a turbine, and generates electricity. So in effect, this is a giant battery. What's really remarkable about this is the electricity is dispatchable in very short order. The underground storage caverns that are used for storage have the necessary capacity, because you do need a large capacity. They are safe from inclement weather, changing temperatures, vandalism, terrorism. They're just an unbelievable resource. And it's a very reliable technology that we've had around for 70, almost going on 80 years. So currently what we are looking for are ways to store excess electricity that's generated by wind and solar primarily, but it could be nuclear, it could be other methods. Right now, there are only 2 diabatic utility scale and 1 adiabatic case plant that provides 1.7 megawatts of peak power. The question is, why, if it's so great, do we not have these everywhere we have excess electricity and underground salt? Well, let me run you through what this quick image is, and then we'll discuss that. You can see here the power in during charging time goes through the motor, which engages the compressor. You cool the air down, you put it in the cavern, you hang on to it until you need it. Then you release the air as it's needed during those peak times. You add some fuel to the combustion chamber to heat up the air, which spins the turbine, goes through the generator, and the power goes out during discharge. So it's actually a remarkably straightforward process. All right, so Huntorf then came online in 1978, uses a nuclear source nighttime power to compress and inject the air into the two caverns. It transfers that off-peak energy produced by base nuclear, or if you had coal, for example, Germany is using coal as well, but this particular plant uses nuclear to those high demand periods. Huntorf, Germany has a 290 megawatt plant, is what was commissioned in 1978, and they upgraded in 2006 to 321 megawatts. So that's a pretty significant battery that they have access to. And it can provide power to the grid with dispatchable electricity in 6 to 9 minutes. So as you're looking at this graphic on the right, you can see through a 24-hour cycle where the air is going to be compressed and the power is generated, and then where it's expanded, which means it's released to cover peak needs. And so it can go back and forth during the day even. It's not required to stay at a certain point in time. All right, so moving on. Okay, so this is a text-heavy slide, but I wanted to make sure you all had the key innovations and challenges associated with this. So these two caverns were planned at Huntorf for various reasons, even though one cavern could have handled the volume. And for perspective, a cavern, depending on how much has already been developed versus not, can run you, if we're talking greenfield, it could run you on the order of 100 million all the way up to 500 million US dollars, again, depending on the size and the scope and how much you involve. So the limiting factor for these caverns really is that CapEx expense. So these two caverns were planned, and they did two instead of one because they wanted redundancy for maintenance and cavern shutdown. It's also easier to refill after drawing down pressure because they are smaller. And then the startup procedure for the plant compressor requires a minimum of 13 bars in at least one cavern. So if you have a drawdown on one and the other's out for maintenance, you still have enough capacity in there to run your case system. The cavern depth was selected to ensure stability for several months at atmospheric internal pressure. Cavern wells needed to be able to handle the extremely high withdrawal rates. These are very fast, combined with low pressure losses. And just as we talked about, these salt caverns are virtually impermeable and they are massive in size. So both of those components or attributes are ideal. As I mentioned, this is a capital intensive project. They are expensive. And one of the challenges, of course, is going to be that the water saturated compressed air is very corrosive. So for your metallurgy downhole, this can be a problem. Your production string was initially made out of normal structural steel with extra thick walls. It had spirally welded production strings that were hung 80 meters in the cavern without support. That's a lot of weight. And they also did this to prevent any salt dust from entering in the turbines, which again would have contributed to corrosion. The 600-meter cavern depth ensured that the air's stability through the seasonal temperature changes would remain the same, and then guaranteed that the specific maximum of pressure required at 100 bar would stay. Lastly, one cavern is cycled daily and the other serves as a backup when the nearby nuclear plant goes offline. So terrific system, redundant, very, very effective. So here we are, we're down to the last slide. And this is one of my favorite graphics on the right, so that you can contemplate while we're talking. I wanted you to understand when I talk about how massive these domal salt caverns are, this is an actual salt cavern on the left, and on the right is the Empire State Building. Now, what you're looking at the domal salt cavern on the left, you'll see a black outline and a green outline. What that is the green was the original size of the cavern, and then we went through and did a rewash, which expanded the size, meaning after a time, let's see, the first one was in 2019, and a year later we went back and did a rewash, and so you can see the expanded size of the cavern. So these really are massive underground storage facilities that, frankly, if they were on the surface, would not only be expensive, would be a tremendous threat for somebody who was a bad actor. So we need the long-term stability of the underground storage of caverns. They can be used with air, natural gas, or hydrogen. They are an efficient use of electricity for compressed air energy storage. The downside really is that caverns are expensive. What I would consider, and one of the reasons I wanted to showcase this today, is because we know energy costs are going up, electricity prices are increasing. We want to be able to capture that unspent electricity. And we also know when it comes to battery storage that critical minerals and critical resources are under increasing pressure from the entire electrification goal in the global economy. So if we can develop a storage mechanism for electricity that doesn't require a whole lot of critical minerals, this would be a fantastic way to take advantage of that excess electricity that isn't being used but is still being generated at night. And then, of course, preserving those peak times for areas and communities during the day so that they are not hit with exorbitant electric bills. So this, my friends, I believe takes us to the end, and we now get to do questions, which I believe some of you have been submitting, so thank you. And I will ask if Sharon, if this is when I leave my screen up or turn my camera on.
Yes, leave the screen on, and if you can open your camera, it will be great to see you. Thank you. So thanks for a great presentation. You can still submit your questions in the question box on the GoToWebinar control panel, and also you can find the presentation slides available to download there. I will start with the first question. Can compressed air energy storage be done in other types of formations besides salt caverns?
That's a great question. So as you recall, we covered the saline aquifers, depleted oil and gas reservoirs, hard rock mines, and right now the one that is considered probably the least attractive is going to be your depleted oil and gas reservoir, because they are also going to have natural gas already entrained in it. So introducing air into that system, there have been questions about whether that could cause that could cause a destructive explosion with having fuel and oxygen under pressure at the same time. You also need to consider with saline aquifers and depleted oil and gas reservoirs that you're not pulling out of a void space, but you would be withdrawing through porosity, and you'd be contending with permeability, and of course you'd be contending with impurities in those storage spaces. So those two would probably be less desirable. The next one after a salt cavern would be hard rock cavern, and that would be my geologically engineering speaking, that would be my second choice if we couldn't go with the salt caverns.
Thank you.
Great question.
The next question is, are you looking at underground hydrogen storage as well? And do you think we will see a lot of this before 2050?
Sure. So I'll answer the second question first. Do I think we'll see a lot before 2050? This will be determined by the market. So it's not simply a matter of supplying the hydrogen. There also has to be people willing to pay for it, and they need to be pretty close in price for a meeting of the minds if they're going to make that work. So that part is beyond me. That's for an economist smarter than me. We absolutely do hydrogen storage. In fact, the 3 hydrogen salt caverns that have already been developed in the US were developed by my company, WSP Energy Storage Services. And we are also doing the ACES project in Delta, Utah, where they have a world-class bedded salt that is so pure it's on the same order as a domal salt. So so that will allow us to store a pretty darn significant amount of hydrogen there that will be used to combust and generate electricity, which will then be sent to LA. So they'll send it down high voltage transmission wires.
Thank you. What is the typical efficiency of compressed air energy storage?
Because it uses, I know you'd want a number, and I don't have one on me at this moment, but I can't. It uses the electricity that isn't being used for anything else, and then is able to turn around and spin it right back. It has a ridiculously high efficiency rating, but let me see if I can find an exact number for you. I know that's one of the main advantages and why it's been so attractive for so many people and so many companies. We did many studies for a variety of interested parties over the decades, frankly, because we've been associated not only with this project, Huntorf, but also McIntosh in Alabama. And that was done in 1991. So there's been a tremendous amount of interest in this because of the efficiency, and it unfortunately just really historically has been low natural gas prices, low electricity prices, coupled with expensive cavern development prices. The numbers just hadn't penciled out yet.
Thank you. There are a lot of questions coming through. The next question is, are there any examples of horizontal caverns with multiple wells used for underground storage? And also, what are the limitations for horizontal caverns?
So limitations for horizontal caverns are going to be how, if you do salt, how do you leach it, right? So if you have, I'll use my pen here. I'm in a hotel room, by the way. I'm on a business trip when we had this scheduled. So so we'll make do, right? This is what engineers do. We make do. So if we'll start this way. So if you have a vertical cavern, you leach down and then you can just flush the water right back out. But if you have a horizontal cavern, you need to develop a way to leach horizontally, and this, I think it could be done, right? But it's not going to be as fast, and the volume isn't going to be quite as large. And what you'll have to be very cognizant of is any sort of preferential leaching underneath what your initial well bore is. So I have heard of companies interested in doing this and developers interested in doing this. One way would be if this is your horizontal cavern, you could drill here and you could drill here and you could drill here and here, right? Now, you know, drilling's expensive, but you could almost make this like this necklace sort of connection all the way down. And so you keep, instead of trying to do the entire length, you keep this distance much shorter. And then that would allow you to inject here and then flush out here, and then inject here and flush out here. So it wouldn't be a perfectly cylindrical cavern, but it, in my opinion, if somebody were willing to take the plunge, I think it actually could be done given the right constraints. So yeah.
Fantastic. I love the example with a pen. I will take the last question. I know we're over time and we have still many questions coming through. How would the compressed air energy storage work using renewable energy?
Okay, so this is something that this is actually, that question is the reason why I wanted to present on this today. And the initial thought would be, can you hook up a compressor to a wind turbine? Can you hook up a compressor to solar panels, right? And just bypass all the middlemen and just have it right there? The short answer is no, you cannot do that. And what you have to do is you have your wind turbines or your solar panel farm, and you have those renewable energy, electricity generating components, putting it right on the grid. Then you take that electricity from the grid and you use that for your compressor. Compressors require an enormous amount of energy for the horsepower that's also required to compress air or any other gas. So it's not enough to just connect it straight to wind turbines or solar panels. You do need to have your compressor, if you're looking for renewable a renewable component, you still need to have it connected to the grid. And if not, of course, you can run your compressor off of diesel or natural gas. And I think they're looking at developing, if they haven't already, compressors that can run off of hydrogen. So for now, with the state of technology and the way that our grid and our system is set up, you have to have your compressor connected to the grid, but you can have that grid supplied by your nuclear fuel, your nuclear generated electricity, or wind or solar.
Fantastic. Thank you, Scyller, for a fantastic presentation. Sorry, we're a bit over time. Thank you all for those who submitted all your questions and also comments. Scyller will be able to reach out to you later by next week with some answers to all your questions. So appreciate again everyone's time. You can find Schuyler's details on the screen here, and you can reach out to her for any additional questions. So again, thanks everyone for joining us today, and we hope to see you in our upcoming sessions.
Send me a ping on LinkedIn. That'll be fun. I'd love to hear from you. Thank you so much. Thank you, Sharon. This was great. I loved it.
Thank you. Thanks, everyone. We'll wrap up the session now. Thanks.